Find minimum and rotated sorted array. Suppose an array of length n, sorted in ascending order, is rotated between 1 and n times. For example, the array nums 0, 1, 2, 4, 5, 6, 7 might become 4, 5, 6, 7, 0, 1, 2, 1, 0, 1, 2 if it was rotated 4 times. 0, 1, 2, 4, 5, 6, 7 if it was rotated 7 times. Oh, like shuffled. Rotated is a weird way to say it. Notice that rotating an array one time results in an array a n minus 1, a0, a1, a2. I see. Okay. Given the sorted array, nums of unique elements return the minimum element of this array. You must write an algorithm that runs in O log n times. Given the sorted rotated array nums of unique element, return the minimum elements of this array. So this array can be rotated. And I guess the question becomes, well, actually, so this is the question. Okay, we gotta find return the minimum element of this array. And find minimum. We see the examples here. Nums 3, 4, 5, 1, 2. Output 1. The original array was 1, 3, 4, 5, rotated 3 times. Okay. And nums, the original array was 0, 1, 2, 4, 5, and it was rotated 4 times. Yeah, output 1, output 0, output 11. Okay. I mean, so we know nums is unique, has unique elements, it's ascending order. We know it's a list of integers, don't know what its size can be. Dichotomy, so can't have duplicates. Ascending. Order is it's sorted, but rotated sorted, so it's a bit of like an exception case. Boundaries. Like these are like the assumptions I'm thinking of, and I would clear up with an interviewer. N is equal to nums at length 1. Okay, so it can only be 1. 5,000 negative to 5,000 positive. Unique, num is sorted, rotated between 1 and n times. So the goal is to do log n times, so we can't just simply rotate, right? Like the kind of doing this on paper, I would honestly, like, if I see a thing, I mean, I can also look through all the elements and see which one's minimum. So just do a search, but that's linear time complexity. We want to log n time. Same thing if you want to just rotate and keep track of like a minimum. I feel like that's more work, to be honest, but to keep track of the minimum value you see and then rotate until you get the minimum value. But again, that's still linear time. So log n time, I know it's going to utilize some kind of binary search trick. And the idea of binary search, I did the binary search question before this, which I totally forgot, by the way, but you have a left pointer, right pointer at the ends, and then you look at the middle, right, of that left and right pointer. Go into the middle, because you know it's sorted, if, and you're given like a target kind of integer to find within this array. If you know that the value in the middle is less than the target, then you know all the elements to the left of that middle value are irrelevant because they're all smaller than the target. So you only need to search in the second half of the array. The same kind of explanation goes for if the element in the middle is larger than the target, right? Then any of the values in the second half of the array are not going to be relevant because all of them are going to be larger than the target. So you can look in the first half of the array that have smaller elements and potentially the target. Now here we don't have a sorted array, but we have a rotated sorted array. It's a weird one. Now how can we optimize this? Like what can we, like what can I, like I'm currently in the brainstorming phase. I've thought of like pen and paper, brute force. Now the optimal solution, which should be O log n time. I know this is a binary search question, but log n time does imply binary search, kind of trees, something along those lines, where basically you have like 16 steps, then you can cut it by half to like 18. And if you have an array, right, basically you come into the middle and then get rid of like an entire like half, and then you come to the middle again, right, and then you get rid of like another half, and then you come in the middle again. Like you get what I mean. Oh my god, you did not see that line. Oh my, okay, well we'll forget I can draw. I'll just come down here. So with this array, it's rotated. What does that tell us? It's rotated. I don't know what writing out rotated will actually do in terms of my understanding, but I wrote it out. We know it's after a few, like 1 to n steps, we know that we can sort it. Sorry, like after 1 to n rotations, we know it will be a sorted array in ascending order. What if we add apply the binary search on this? Like how many rotations we need? So if we need, I'm trying to think, 1 to n, and we choose the value, so left pointer, right pointer, we choose the value in the middle. Wait, so is it always a rotated array? Like, I checked the assumptions and everything. Suppose an array of length n is sorted, is rotated between 1 and n times. Okay, so at least 1 time it's rotated. Okay. And we come here, 1 plus n divided by 2, that's the midpoint. But then wouldn't we have to do this number of rotations as well? I guess we don't really need to rotate actually. And then, so in the binary search we had like a target. Our target is like a minimum. Okay. We want the minimum, min. So if you start at the left and right, does it change anything if we know whether the left is a little smaller than the right, or vice versa? Does that help us with anything? So if I were to take, I'm just going to take this as an example. That is so small, oh my god. I'm just going to make that. There we go, beautiful. Okay. So if we know right is smaller than left, does that mean that we should stay in this corner and not stay in this corner? Does that help with anything? Kind of actually, because I mean, if we know this is larger, we're looking for the minimum. Staying in the right side should be helpful, right? We can kind of keep track of the minimum, like the target, like a target min, and if we kind of come into here, go into the middle, and realize, like, imagine this is one right now, but let's say we have another array. I'll say like 5, 7, 9, 15, and 4, right? Left, right. We kind of go into this part of the array. We see this. But notice that this is actually bigger than the 4, then we can actually go into the middle here, right? Kind of something like that. That looks like a Pokeball. Yeah. So not exactly doing it on the number of rotations, like implicitly doing it, but not like explicitly rotating the entire array. That wouldn't make sense. When we can actually just like kind of do like a index manipulation, really. So yeah, let's start off with the right, left, and right, and depending on which one is smaller, we go with that. Well, okay, let's take a look at an example where it's not smaller. I'm sure there's a example here somewhere. Well, okay, hold on. So this example here, I'm going to expand on that. And the integers can be negative, yeah. So 11, 13, 15, 17. So this is ascending order. We know this is already the middle. So if it's left and right, do we just like check over here and then do the whole middle thing? But then we know it's ascending from here, right? Right? We know it's like going to be ascending overall. So I mean, if left is minimum, then that doesn't change anything. Because then we don't even need to look all the way here. We know immediately 11 is, oh my god, 11 is 11 is the minimum. Is that correct? Not necessarily, actually. Hold on. Look. 11, 13, 15, and like 1, 17. Does that make sense? No, it does not. Okay, so that's not possible. Hold on, give me like 2 minutes. I'll be right back.